Let's try to understand the physics of a bird's wings. The shape of a wing of mass m can be approximated as a right triangle, as shown here. The two sides of the right angle have length a and b, respectively. The coordinate system is also set up in the figure. Where is the center of mass of the wing? So, if you remember, the center of mass of any object is given by 1 over m, where m is the total mass, times the integral of r, or the distance. This r is the distance of each point from the axis, or the axis of rotation, dm, times each little mass that part has. So that's the expression for the center of mass. So if we think about this bird's wing here, so here we have our axis, and here we have the triangle. So if that is A and this part is B, we can divide this up into a bunch of little rectangles. You can divide these into a bunch of little rectangles, and the height of each rectangle is given by the y-coordinate of each little rectangle. And we can find what the function that should give us this y. So if you remember, you can write an equation for a certain y value by saying that y equals mx plus b, where m is the slope and b in this case is the y-intercept. So our slope is going to be the change in y over the change in x. So if this is the y-axis and this is the x-axis, that's the x-axis, then the change in y over the change in x is simply going to be a over b, since your rise is, or change in y is a, each little distance a, and your change in x is b. And this is going to be negative because the slope is negative. And then, of course, the y-intercept is going to be a. It intersects the y-axis at a. So the y is going to be equal to a minus a over b and x times x. I forgot this here, but it's times x. So this is our function that gives us the y-coordinate of each point, or each tiny, like very small rectangle. And that is going to be here. So that is the height of each little rectangle. So we know that the x-coordinate for the center of mass is equal to 1 over m times the integral of each x position times its little mass, dm. And we're going to add them all together, add all of these infinitely small pieces together, which is what the integral means. And we cannot integrate with each little change in mass, because that's just not how, we can't just integrate a distance with a mass. So we need to convert this into a little change dx instead. So we know that each little mass, or dm, over the total mass of the bird's wing m must be equal to each little area dA of each little rectangle that we've divided it into. And just note that these rectangles will get smaller and smaller as you add infinitely more of them. And that is the same as the little fraction dA, the area of each little rectangle, over the total area A of the whole wing, which in this case is this right triangle. And the area, or A, of a right triangle is given by 1/2 BH. And in this case, the base is still B and A is the height. So it's going to be 1/2 AB. And that's the total area of our triangle. And to figure out dA, or the area of each little rectangle, we can say that the width of each tiny little small rectangle is a very small length dx, and each height is what we calculated earlier using this function, is the y-coordinate of the top of each rectangle. So the height of the rectangle is going to be given by this. So the area of each little rectangle is simply going to be its width, which is dx, times its height, which is this value here. So it's going to be h dx, where h is the height, and h, as we calculated here, is going to be a minus a over b x dx. And now we've actually got something that we can plug in. So I'm going to erase all of this to make some more space here. So if we solve for dm, this becomes each little mass dm is equal to the total mass m divided by the total area a, which is 1/2 AB, as we calculated here, times the area of each little rectangle, which is given by dA. And again, we also calculated that dA is equal to a minus a over bx times dx. So dm is going to be equal to 2 times the total mass divided by a times b, and then we're going to substitute our value for dA. dA is times a minus a over b x. Okay, so I'm going to make this area a bit smaller, get rid of that. A minus a over bx dx. And now we have this expression that we can actually substitute in for dm in our integral above. So dm is equal to 2 times the total mass divided by a times b times a minus a over bx dx. And I'm going to substitute this back into our integral up there. So let's get rid of this. Don't need to get rid of that yet. Just trying to erase all of this. Okay. So, substituting, get that the center of mass, or the x-coordinate for the center of the mass, is equal to 1 over m times the integral of x times 2m over ab times a minus a over bx dx. And notice we can factor a out of here to get a times 1 minus 1 over bx here. So if I replace this part here with that, okay, it is 2ma over ab times 1 minus 1 over bx dx. And that is the integral that we have to evaluate after plugging in our value for dm. The a's cancel out, and we can move 2m over b outside because it's a constant. So the masses inside and outside cancel out. So you're left with 2 over b times the integral of x minus x squared over b dx. And again, I distributed x over this part here to get this. And now I didn't specify this yet, but our limits of integration are from 0 to b. It's from 0 to b. Since we're evaluating each the position of each point times the mass from the y-axis, so we're evaluating this along the entire length of the wing in the x direction. So this becomes 2 over b. This is times x squared over 2. Integral of x is x squared over 2. And the integral of x squared over b is x cubed over 3b. And we're evaluating this from 0 to b. So I'm going to make some more space here. Get rid of all of that. Get x cubed over 3b. And we're evaluating that from 0 to b. So because if we plug in 0 in, this whole expression becomes 0. It's simply equal to this equation evaluated at b. So this becomes 2 over b times b squared over 2 minus b cubed over 3b. And then we can just simplify this a little bit. Get 2b squared over 2b minus 2b squared over 3b. And again, one of these b's canceled out, so that's what I did. And now if we come back down here, the 2's cancel out, one of the b's cancels out. You get that b minus 2/3 b, and that is equal to the center of mass, the x-coordinate for the center of mass. So evaluating this, you get that the center of mass, the x-coordinate for the center of mass, is simply equal to 1/3 the length of b, which is like going to be around, right around here. So if I write it down, the x-coordinate for the center of mass is equal to 1/3 the length of b. And that is it for our x-coordinate. But we're not done yet, since we still need to figure out the y-coordinate for the center of mass. And again, that is equal to 1 over m times the integral of each point, which is on the y-axis with respect to each little to the mass of each little point or each little cell. And this time we're integrating from 0 to a, since we're integrating along the y-axis. And again, we have to replace dm with an expression, which I'm pretty sure was m over a, the total mass over the total area, times dA, which the total mass over the total area became 2 times the total mass over a times b, because the area equals 1/2 ab, and we substituted that in. And that is times dA, which is the area of each little rectangle we divided it into. And again, if I draw this triangle again, the only thing different is that we're making rectangles along the y-axis instead of the x-axis. So the height will be the function, will be given by the function of this line, which, if you remember y, we can say that it is x is equal to my plus some sort of x-intercept b. So the equation for the line becomes the slope, which in this case is the change in x over change in y. So it's the reciprocal. So if this is a and that is b, the change in x becomes b, and the change in y becomes a. And again, this is negative. There's a negative slope here. And I'm going to add the x-intercept, which is at b. So this becomes b minus b over a. And this is going to be y times the slope y. And so this becomes b times 1 minus 1 over a y. Like that. And that is our equation for the height of each little rectangle. And again, the area of each little rectangle dA is given by the height of each little rectangle times a very small length, which was dx, which was the width last time, but this time it's going to be dy, since it's a very small part of the y-axis. So if we substitute everything in, we get that dA is equal to the height, which is b times 1 minus 1 over ay dy. So that is what dA is. And now we plug this back into here. to get that dm is equal to 2m b over ab times 1 minus 1 over ay dy, and the b's cancel here. So now we can substitute this back into our integral. So the y-coordinate for the center of mass is going to be equal to 1 over m times the integral of y, and dm is 2m over a times 1 minus 1 over a y dy. And now again, we just need to evaluate this integral again, which is almost pretty much the same thing, but just with the variables reversed. So again, the masses cancel, so you get the center of mass, the y-coordinate for the center of mass is going to be equal to 2 over a times the integral. And again, this is from 0 to a, since we're integrating along the y-axis this time. And this is 0 to a of y minus y squared over a dy. So this gives us 2 over a times y squared over 2 minus y cubed over 3a. And we're evaluating this from 0 to a. And if you look at this, this is almost the exact same thing as what we had earlier, just with a instead of b. So if you evaluate this, you get that the center of mass, the y-coordinate for the center of mass, is going to be equal to a minus 2/3 a. This is if you plug in a for the y's and evaluate. And so this will give us our answer of 1/3 a, which is the exact same as the answer for our x-coordinate for the center of mass, just along the y-axis instead. So that's our y-coordinate for our center of mass of the bird wing. So the center of mass of the bird wing is given by 1/3 the distance, the length of b, as the x-coordinate, and 1/3 the length of a as the y-coordinate. So this is going to be something like around here, I guess. If this is a and that is b, this is going to be the center of mass, somewhere around there. And that is how you would solve this problem here.